Hi everyone, this is the video recording of our paper called Recovering Communities in Structured Random Graphs. And this is joint work with Michael Kapralov and Luca Trevisan. So in the community detection problem, we are given as input a graph, and our task is to recover the communities. And what are communities? Well, these are just sets of vertices that are internally well connected as induced subgraphs, but that have few edges going to the rest of the graph. And the community detection problem is a classical problem in graph algorithms and has been studied in many models. For example, in the stochastic block model, two vertices are connected by an edge with a certain probability p if they belong to the same community, and with a lower probability if they belong to different communities. And there are also worst-case analogs of this, in which you assume that the graph is partitioned into expanders, and that these expanders are connected to each other by a small number of edges. Now, what's in common for all of these models is that they assume that the communities are disjoint. Okay, so they assume that the graph can be partitioned more or less uniquely into communities, such that each vertex belongs to exactly one community. But now, if we think about real-life graphs, then this seems like an unrealistic expectation. Because for all we know, the graphs could have many different communities, and these communities could be overlapping. So this leads to the question, if we have a graph where the communities overlap significantly, can we still recover the community structure? Now, the most basic example of a graph that has an overlapping community structure is the hypercube. So the d-dimensional hypercube graph is the graph that has 2 to the d vertices, and these will be the points in the Boolean hypercube. And 2 vertices are connected by an edge if their Hamming distance is exactly 1. So here in the diagram, you see a 3-dimensional hypercube graph. Okay, and this is a graph with degree d. And the hypercube graph has exactly d sparsest cuts. So you can think of it as d different communities. Okay, and these are the coordinate cuts. So what is a coordinate cut is just you pick a coordinate between 1 and d, and then the ith coordinate cut will be the cut that separates the vertices that have 0 in that coordinate from the vertices that have 1 in that coordinate. Okay, and the coordinate cuts have size 2 to the d minus 1. Okay, so here in the diagram, one of the coordinate cuts would be the one that puts the vertices in one of the pink sets on one side and the vertices in the other pink set on the other side. Or the blue partitioning would be a different coordinate cut. And then finally, the last coordinate cut would be this orange partitioning. And note that the coordinate cuts are maximally intersecting or maximally overlapping. In the sense that if I take any 2 coordinate cuts, then the symmetric difference of them is going to be exactly half of the vertices. Okay, so if I'm given a hypercube, then it is easy to recover the coordinate structure. I can just find it from looking at the structure of the hypercube. But now, what if I subsample the hypercube? Okay, so what if I do the following? I start with a d-dimensional hypercube, and I include all of the vertices, but I subsample the edges at a rate p, which is less than 1. Okay, this gives me a random graph, and furthermore, I will think of the vertices as unlabeled. Okay, so I don't see them with the Boolean hypercube labels, I just see them as unlabeled vertices, together with some edges, which are the edges that I subsampled. So now the central question, which we are considering in this paper, is if we're given this unlabeled subsampled hypercube, can we recover the coordinate structure? Can we learn what the coordinate cuts were in the original hypercube that it was sampled from? Now, this of course depends on what rate we sample with, but our results will work all the way down to the sampling rate being log d over d. Okay, so this corresponds to having expected degree log d, or log n, where n is the number of vertices. And note that in this setting, we will have a 1 over poly d fraction of isolated vertices. And for these vertices, we don't have any edges incident on them, so we don't have any information about them. So in particular, it's not possible to determine which side of the cut these isolated vertices should be on. So therefore, exact recovery is not possible. However, we still show that it's possible to achieve approximate recovery. So what we show is that if we subsample the hypercube at a rate log d over d, then we can recover all of the coordinate cuts simultaneously, such that each of our recovered cuts differs from a coordinate cut in at most a 1 over poly d fraction of vertices. And our result is algorithmic. So we give a deterministic algorithm that achieves this recovery. However, our algorithm runs in exponential time. But what about exact recovery? Is it ever possible to achieve exact recovery? So in the stochastic block model, we know that if we are in the regime where the expected degrees are logarithmic, then it is possible to achieve exact recovery. But now, in our case, the hypercube is already a very sparse graph. So even before we started the subsampling, each vertex had degree d, which is logarithmic in the number of vertices. So this suggests that if we want to achieve exact recovery, we should start off by sampling from a denser graph than the hypercube. So motivated by this, we will consider the k-distance hypercube. So the d-dimensional k-distance hypercube is going to have exactly the same vertex set as the hypercube, but now we will connect two vertices to each other if the Hamming distance is exactly k. So in the hypercube, we connected them if the Hamming distance was 1. Now we connect them if the Hamming distance is exactly k. And this gives us a denser graph, okay? Because this graph has degree d choose k, which for constant k is roughly d to the k. Okay, and we show that if we subsample the d-dimensional k-distance hypercube at a rate log d over d to the k minus 1, then with a high probability over the subsampling, we can recover all of the cuts, coordinate cuts exactly. And again, our result is algorithmic. So we give a deterministic algorithm that achieves exact recovery. But again, the algorithm will run in exponential time. So for the rest of the talk, I will sketch the proof of our main result, which is the approximate recovery in the subsampled hypercube. Okay, so let's start by understanding how to recover one single coordinate cut. And then we will later see how the same ideas can easily be extended to recover all of the coordinate cuts simultaneously. So if I just want to recover one coordinate cut, then the most obvious thing I can do is to just take the sparsest balanced cut, where by balanced, I mean that it puts the same number of vertices on one side of the cut and on the other side of the cut. But does this work? So before I subsample, I know that the sparsest balanced cut is exactly a coordinate cut. But what if the hypercube has other sparse cuts, which are far away from the coordinate cuts? If this happens, then this is very dangerous for us, because now these other bad cuts can become the new sparsest cuts after we subsample. So we need to show that this doesn't happen. Okay, so let's try to understand what sparse cuts look like in the hypercube before we subsampled anything. And for this, it will be convenient to view cuts as Boolean functions from the hypercube. Okay, so for any cut S, just think of it in terms of the indicator function that maps each vertex to 1 if it's on one side of the cut and 0 if it's on the other side of the cut. Now, it turns out that the size of a cut is proportional to the influence of the indicator function. Okay, so in particular, I can express the cut size in terms of the Fourier coefficients of the indicator. And note that the higher level Fourier coefficients are penalized at a higher rate in this expression. So this means that if I have a sparse cut, then it has to place most of its Fourier mass on the lower coefficients. And more concretely, we can show that if a cut is sparse, then it places almost all of its Fourier mass on the bottom two levels. So on the 0th level and on the 1st level. Okay, so in other words, every sparse cut in the hypercube consists almost entirely of the constant terms and the linear terms. And now we can apply the classical result of Friedgut, Kalai, and Noir, which I will refer to as the FKN theorem, which says that if I have a Boolean function on the hypercube that places almost all of its mass on the bottom Fourier coefficients, or the bottom Fourier levels, then this function is close in Hamming distance to a single coordinate cut. And this is exactly what we needed. Okay, we saw that every sparse cut places almost all of its mass on the bottom two levels. So now the FKN theorem tells us that every sparse cut has to be close to a coordinate cut in Hamming distance. And note that the theorem of Friedgut, Kalai, and Noir is highly non-trivial. So if we remove the assumption that the function is Boolean and instead considered any real-valued function on the hypercube, then the theorem statement would have been false. Okay, so in particular, the theorem does not apply to SDP solutions. And this is because I could take any convex combination of coordinate cuts, then this would give me a function that places all of its mass on the bottom two levels, but this function is not close to any coordinate cut. Okay, but luckily we are not considering SDP solutions. What our algorithm will do is it will enumerate over all possible cuts, which are Boolean functions, and so the theorem applies. Okay, so now that we know that before subsampling the sparse cuts are close to coordinate cuts, what happens after that we sample? So remember, our goal is to show that the sparsest balanced cut differs from a coordinate cut in at most an epsilon fraction of the vertices, for some epsilon equals 1 over poly d after the subsampling. And by the FKN theorem, we know that if we have a bad cut, by which I mean a cut which differs from all of the coordinate cuts in at least an epsilon fraction of the vertices, then we know that this cut can't be too sparse. And more concretely, we know that it has to be a 1 plus O of epsilon factor larger than the coordinate cuts. So this means that it would be enough for us to show that all the cuts are preserved up to a 1 plus minus epsilon factor after the subsampling. So how would we try to show that? Well, we could try to apply Karger cut sparsification. So what is Karger cut sparsification? It tells us that given any graph, if I subsample it at a certain rate, then all the cuts will be preserved up to a 1 plus minus epsilon factor. But now what happens if we try to apply the theorem or Karger cut sparsification to our setting? Well, for us, log n is equal to the number to the d, and the min cut is also equal to d. So in other words, in our setting, the theorem only applies with a sampling rate which is higher than 1. So we can't use that. What we will do instead is that we will apply cut sparsification, but not on the entire cut, but rather on the symmetric difference of cuts. So what do I mean by that? Well, suppose that S is a bad cut, in the sense that it's far away from all coordinate cuts, and let Si be the coordinate cut that is the closest to S. Okay, so here in the diagram, S is drawn as this red shape, and the coordinate cut Si is drawn as the two rectangles. So one of the rectangles represents the vertices that are on one side of the coordinate cut, and then the other one represents the vertices on the other side of the coordinate cut. Okay, and observe that in this case, we only need to show concentration for the edges that are incident on the two small blue sets. Okay, so we just only need to show concentration for the blue edges. And why is that? Well, note that any other edge in the graph, so any other edge which is not one of the blue ones, contributes equally much to the cut S as to the coordinate cut Si. Okay, so in particular, whether or not these other edges get sampled don't influence which of the two cuts became the smaller one. So I just need to show that the blue edges concentrate well. Okay, now suppose that the red cut S had size 1 plus epsilon times 2 to the d minus 1 before I subsample. Then we can show that the size of the blue cut is O of epsilon times 2 to the d minus 1. So in other words, it's just an O of epsilon fraction of a coordinate cut size. And therefore, it is enough to argue that the blue edges concentrate up to a constant factor, as opposed to a 1 plus minus epsilon factor. And now this we can achieve using ideas from cargo cut sparsification. Okay, and that way we get that after the subsampling, the red cut S is still larger than the coordinate cut, and so we conclude that the sparses balanced cut is indeed close to a coordinate cut. So this tells us how to recover one cut, but now what about recovering all cuts simultaneously? Well, to recover one cut, we just took the cut that minimizes the number of edges crossing it. So to recover all D cuts, we will take a set of D cuts that minimizes the sum of number of edges crossing the cuts. But we also impose the condition that the symmetric difference of any pair of our cuts has to be 2 to the d minus 1. Okay, this ensures that the D cuts that we pick are going to be very different from each other. And now we know that in the optimal solution, each of the D cuts has to be small. So it has to be close to a coordinate cut. And because our D cuts are very different from each other, it means that each of them has to be close to a different coordinate cut. And that way we recover all of the D coordinate cuts. And the way we solve it is just directly by direct enumeration. So we try all of the feasible solutions and pick the best one. So just to summarize, we show that if you subsample the hypercube, then the coordinate structure is, or the community structure is preserved, and you can recover all of the coordinate cuts. However, our algorithm for achieving this runs in exponential time. So a very interesting open problem is to construct a polynomial time algorithm that achieves the same guarantees. And more broadly, it would be interesting to study more broad classes of graphs, so not just hypercubes, and try to understand if the structure is preserved under subsampling. Thank you.